Uh, so good afternoon, everyone. This is the final week of the semester already. So we just have one last topic to talk about today, and so probably we'll finish everything, the final topic of this syllabus today. And so the plan for the remaining few days of the semester is we're going to talk about polarization today, and then there's a few things that actually I didn't have time to finish when we are talking about the interference, about the phase differences and things like that. Because if you have been trying the tutorial questions, the last two questions are a bit challenging, right? Or if you use the method I've been telling you, it's actually not that bad. So I'm going to talk about those things after we finish this topic. So that will be the first and second part of today's class. And then for the last class this Wednesday, I will because we still have one more day of class, and I will say something interesting that it's gonna be a bit more complicated in mathematics sense, but it will not be examinable. What I plan to do on Wednesday is to connect what you have learned in your calculus 2 and use it to rewrite the Maxwell's equation. So that thing is already in the lecture notes already, but you may have noticed that I skipped that part when we were talking about Maxwell's equation, and it's because it's not examinable. But since we have time and it's interesting and it is important, because even if you're skipping it now, it's not examinable now. If you're taking the next electromagnetism course in the future, that you cannot avoid it. So I will give you a bit of a preview on how we apply the calculus 2 methods to Maxwell's equation, and then to give you an idea of what Maxwell's equation is about, right? I keep saying it's kind of amazing that all this theory come from 4 equations, so we're gonna explore those ideas. So Wednesday is more of a fun type of class that is not examinable, and also of course we will do whatever remaining tutorial questions that we have left on Wednesday. So that was for Wednesday. And also remind everyone again, this Friday is the due date of the assignment, so keep that in mind. Don't forget, right? Assignment, one last thing for this Friday. Yeah, next sem, I hope next time we get physical class. Yes, I told you, I mentioned this many times before, right? I miss conducting the class using the whiteboard rather than talking on the camera. Yes, to read the gradient part. You haven't finished. You mean the assignment, right? Yeah. So 5 more days, plenty of time, I guess. I don't know. Yeah, plenty of time. 5 days. So those are the important things, right? And then after that, it's gonna be the exam already. So exam is gonna be I already answered this question before. Exam is gonna be the same format as the midterm. So 2 hours, and then upload the question to the Moodle. You get your questions from there, answer them, and then take the picture or scan, and then the PDF file you submit. So everything the same as the midterm exam. What else? I think that is the important thing to cover for now. Claim with the school for physical class. So Prof Xiongshi mentioned Maxwell's equation using divergence, is it? So you guys are learning divergence theorem around now? Yeah. I think there's gonna be a pro-cons there's gonna be some pro and con if we go back to physical class, because right, if physical class, I will be talking on the whiteboard, so there's not gonna be a paper that I will scan and upload after the class. So everyone is okay with that, right? Then that means if it's a physical class, you guys must really copy from the whiteboard. So that is probably the difference, one of the main differences. And of course there's gonna be no recording, so you cannot rewatch the recording. I don't know how many people have been watching the videos, or just the class by itself. Yeah, copy paste using your pen, the traditional way. Yes. Yeah, like a lot of universities are doing the a lot of universities are having the ceremony around now, July. So put on camera, and then some get the clothes. I don't know, some get the clothes sent over or something. You know, the this kind of thing. But I think for you guys, no need to worry. I don't believe we will be the pandemic all the way until 3 years from now. So maybe next year physical class, and at least you guys will have the physical ceremony, right? So meet up with your friends, wear the thing, and then you hold the thing, yeah, and all these things. Your calculus is quite behind. Oh, is it? Stokes theorem on Friday. Oh, okay. I will mention Stokes theorem on Wednesday. So that means I will actually bring up Stokes theorem before Professor Xiongshi. Interesting. Hopefully you will not be confused. Then that's a good thing we have the recording. So after you learn Stokes theorem on Friday, then you rewatch the video to see how is it being used for Maxwell's equation. Yeah, so a lot of interesting stuff that I want to cover on Wednesday. It's gonna be very, very interesting. But there's one last topic to cover here in the official syllabus, which is regarding polarization. So what is polarization about? There is one more aspect about EM waves that we still haven't studied. Is this one. It's polarization. And polarization just means the direction of the electric field. So we should define it here. Polarization. You may have noticed that I spell polarization with a S because I'm used to UK British English. For those who are using American English, is polarized Z, right? Using the Z, polarization. Polarization is the direction of the electric field. In the EM wave. Okay, so we don't need, because magnetic field we already know is the other perpendicular direction, and therefore we don't really need to we just look at this, right? From this we already know what is the magnetic field, so we focus on the direction of the electric field. Okay, so yeah, so how do I put it? So let me just say this. If the light wave always have a fixed direction, because the reason is because it's not always the case, but if we are talking about this special type of light, and it is the light that is being used for interference experiment, diffraction grating, and things like that. So no, well, not all the time, right? Oh, all the time. So I'm moving, right? Yes. Okay, good. So if the light wave always has fixed direction, then we say is called polarized. Okay. Yeah, so American English and British English, polarization, organization. What is? Yeah, these are the two words that came to my mind. So the obvious example is the light that we have been studying. Actually, they are all polarized. So yeah, for example, the sinusoidal plane wave is polarized, right? And remember, what is the equation for sinusoidal plane wave? Usually I write my axis to be the direction of my electric field, and then I got the amplitude, and then I got cosine kx minus omega t. So this is the direction of the polarization, right? So so that means because this light, we say that the light is polarized in the y direction. So if we draw the wave again, we should be very familiar with this picture by now. if I write it this way, that means my light is propagating along the x-axis, and then my y-axis is here, and then my z-axis, my magnetic field will be here, okay, and then my light is moving like this, okay. And usually when I draw it this way, this is actually just one light ray, and of course this is a plane wave. That means for every other position of y and z, it is going to be there's going to be many copies of it, right? So all of them are in the y direction, right? So it's up and down, up and down. So whether it is positive y or negative y, it doesn't matter. What I'm trying to say is all of them are in the y direction. So usually when I draw the direction of, when it comes to polarization, I will draw it this way, the arrow pointing on both sides, right? So this is the y-axis. So this is my direction of polarization. Okay, so then in general, the direction of polarization doesn't always have to be exactly in the y-axis, right? Maybe it's like it could be at some angle, right? So maybe I got how to say? So maybe I got my y-axis here, my x-axis, and my z-axis here, and my EM wave is actually pointing this way. So I got the light that is like a bit like this. Okay, so let's say the angle is some angle phi. So this is light polarized at angle phi with the y-axis. So in general, the polarization could be in any direction. Okay, so this is what we talk about when we talk about the polarization of light. We start to care about what is the direction of the electric field. Can this interfere? Yeah, yes, this is what I'm going to do next. Yeah, so zebra, I think it's pronounced zebra. Zebra or zebra. That is the Z that is in American and British English. Okay, so yes, you bring a relevant question. Can they interfere? Let us consider the two light waves that are interfering at different polarization. So that is what we will do. Okay, so we will consider the superposition of light that is polarized along different directions. Okay, so yes, so let's say light number one. Light number one is my default example. Is always, I always prefer the y direction, cos kx minus omega t, and let me just mix it with another light that is in a different direction. So just as a way to understand this, let us consider a light in the z direction, so k. Okay, so k e cos kx minus omega t. But to make things more interesting, as we have been learning so far, usually interesting phenomena happens when there is some phase difference. So let us put a phase difference. So these two lights have different phase, and now I want to mix these two together. Okay, so I got a light that is E1 pointing along the y direction. Okay, so this is my x-axis. So this is my sine curve along the x-axis. And then I got E2 that is in another direction that is slightly not in phase. So this is going to be hard to draw. I don't know. So slightly not in phase. So I'm not drawing the same phase here. This is not the magnetic field, right? This is E2. Okay, so I'm not drawing the magnetic field here. So B not drawn here. This is two separate lights that are not in phase. Okay, so what happens if I interfere these two light sources? So let's take E1 plus E2. So E1 plus E2, luckily for us, we don't need to use any trigo formula because these are different directions. So actually these two should not be added up together. you just have two different vector components. So the superposition gives this. Okay. Well, I'm supposed to take E1 plus E2. And E1 was this, E2 is this. So just add them up separately. I got E0. So actually, let us not assume they have the same amplitude. So E1 and E2. Okay. So I have E1, right? Amplitude 1, amplitude 2, right? So I'm not even assuming they have the same amplitude. E1 cos kx minus omega t. This is in the j direction, and then this is in the k direction. So I got E2 cos kx minus omega t. There is a phase difference, and this is in the k direction. Okay, so there is nothing special here. I only got an electric field now that is having two different components. So this is my y component, and this is my z component. Okay, so basically, yeah, so let me just write this. Now we just have an EM wave with y and z components. And each component is a function of kx, of course, and also there's omega t. So each component will oscillate with omega t, right? As time goes on, it will go up and go down because of the omega t. But there's a phase difference. So that is where the interesting part comes in. So each component oscillates with angular frequency omega, right? So omega is just 2 pi f. Okay, so basically what this is, what we're having. So what I have here is actually a vector that I can actually plot this on the y and z axis. I can plot a vector, right? Just like what we've been doing all the way since mechanics. We got a vector, we got the components, and these components are changing with time. So let us see what can we do with this. Okay, so what I'm going to do is I'm going to draw my viewpoint on the x and y axis. So that means if my y axis is here, and if my z axis is here, and my x axis is here, right? So the light is shining in this direction. This component is in this direction. This component is in that direction. So I will draw the projection of the YZ plane. So that means what I'm going to do is I'm just going to look at this in the x direction. So what I'm going to do is viewing along the x direction. So if I look at it from the x direction, I will see the y-axis like this, and I will see the z-axis like this. And if I look at it like this, what does the vector look like? So the vector is having a y component and a z component. So I got this vector E, and then this is having a z component, and this is having a y component, right? So this is E1 plus E2. So E1 plus E2 gives me the total vector. Okay, so that is so this is our vector if I view it from this. So now at a fixed position, right? So if I'm looking at it at a fixed position, the x is fixed, but the time will change, right? Time just runs on. So as time goes on, the angle will change, and this angle will change. So this vector will change position and even change, probably even change length, because this plus this will be different in magnitude because of the phase difference, and it will change in length and it will change direction as time goes on. So we want to study this behavior in a little bit next. Okay, so does this make sense so far? Okay, I don't know what's going on. Interesting. Okay, so let us see what happens. It depends on the phase difference. In fact, we just study two cases only, two simple cases for the phase difference. Okay, so the I should probably write some additional info. The vector E is E1 plus E2 will change direction, length and direction as omega t changes, right? And the actual behavior depends on the phase difference, which we will only study two cases. So the actual behavior oh yeah, this is another British English. OUR. Hang on. Behavior. Right? So American doesn't have the U. Actual behavior depends on phi. So let's look at case by case, starting with case 1, where no phase difference, phi equals to 0. So this is the case where we will call linear polarization. So why is it called that? Well, we shall see soon. So when phi equals to 0, what happens? My y component is E1 sine, cos. I was using cos, right? So cos kx minus omega t, and then my Ez is E2 cos kx minus omega t. So it is the same, right? So the E1 and E2 components, well, they're both having the cosine function. So in other words, what I have here is Ey over Ez. If I divide these two, then it's just equals to E1 over E2, right? The cosine will cancel each other, and it's just constant dividing by another constant. So this is constant. Okay, and therefore I can actually plot the values of Ey is just E1 over E2 times Ez. So what is happening here is that I can actually write what happens to the vector. So my vector, the y component is always constant times the z component. So Ey here, the z direction here, and according to this picture, right, my Ey is always on Ez. So that means my vector is always pointing along this direction. Okay, so my vector is always pointing along this direction. So let me draw this vector. So this is my vector E, is E1 plus E2. Okay, and it is always because the E2 is the amplitude of the second light, E1 is the amplitude of the first light, so it cannot go higher than that. So first light is here, second light is here. Okay, so that means my electric field, what happens with my electric field is, well, the y component is always constant times the z component, so it's always along this line. It's always along this line, and the length is in phase. So cosine omega t, so as time changes, cosine can go from -1 to 0 to +1. So this vector goes from negative direction to 0 to positive and then to negative. So the electric field vector is always pointing along the line. So this is why it's called linear polarization. Can you imagine? Right. So imagine the animation where the vector is pointing always along the line direction, shrinking to maximum to 0 to minimum to 0, right? So it's always along this line, and this is why we call it the linear polarization. Yes, the rotate one is the second case. Yeah, so we will come to that later. This is case 2. We are talking about, this is case 1 here. So the questions you're asking is about case 2. So let's go to case 2 now. Okay, case 2. Case 2 is pi over 2. Okay, so let's talk about case number 2. What happens if the phase difference between the two lights is pi over 2? Okay, so pi over 2, this is called the elliptical or circular polarization. Of course, circle is a special case of the ellipse, so it depends on what is actually happening. Okay, so the phase difference is phi over 2. So that means if I take E1, right, is E1 cos kx minus omega t. This is in the j direction, and then the other one is E2 cos kx minus omega t plus pi over 2, right? So plus the pi over 2 here. Okay, and then this is in the k direction. And cosine of something plus pi over 2 is actually what? Minus, right? I forgot the formula. Kx minus omega t. Is it correct? Right. So this is actually just E1 cos kx minus omega t and then j. Okay. So this is my y component. This is my z component. Well, plus or minus, I can't remember, but it is not important because I'm going to square this function. So notice that what is the y component and what is the z component? Well, we observe that if I take EY, EY square, I will get this thing square. So if I divide by E1, right, I will get cosine square. Okay, so this thing square is just cos square kx minus omega t. And if I take EZ square and then divided by E2 square, I just get sine square kx minus omega t. So if I plus these two together, it becomes equals to 1. So plus the two together, right? EY square plus E1 square plus EZ square plus E2 square is just sine square plus cos square, so it's just equals to 1. Now, does anyone recognize this equation? This is an equation for an ellipse, right? So yeah, so this is equation for ellipse. For the ellipse, I think in your calculus tool, is y squared over a plus x squared over b equals to 1. This is the equation of an ellipse. Just that I'm using the different symbols here. So this is the, yeah, so this is the equation of an ellipse. And we see that the x and y components are the arrow of the vector. So the tip of the vector E traces out an ellipse. Because the y component and the z component of the vector, the x and y coordinates are always on the coordinates of the ellipse. So if I draw it here, it's going to look something like this. Okay, so my y-axis is here, my z-axis is here. So let me put this as the maximum E1 amplitude. Okay, and the E2 in general is not the same amplitude, so let me put this like this, and then it is going to be an ellipse. Yeah, something like this, right? So this is minus E2, this is minus E1. So my vector is pointing like this. Okay, and as the angle changes, right, so the vector will be the pointing along the tip of the ellipse. And this is why we call this the elliptical polarization. You mean you forgot the formula? Why voodoo part is this polarization, is it? Yeah, so in this picture, I'm just drawing a cross section of a fixed this is a picture for a fixed x, right? And of course in the x direction we got many different things. So if I trace out all the vectors along the x-axis, is again is going to be very hard to draw, but it's just the diagram that you are pasted in the chat just now. Okay, so so imagine, yeah, there's an ellipse here. I don't know how to draw. So one vector is here, and then the other vector is going to be here, and then the other vector is going to be here, like this. So we will trace out the line of the helical shape. So I want to make it like this. So let me try again. I hope you get the idea, right? So the vector is pointing here, 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 here. Something like that. Something like that. Why is it? Yeah, it's stuck. Okay, so this is just this line is actually joining the tips of the arrow, and then we follow all the arrow and we got this elliptical shape. And of course one last thing is, why is it called the circular polarization? Well, circular polarization is the special case E1 is equals to E2. So let's just call this E0 is the radius of the circle. So in this case, my light is just on a circle. Okay, so one circle here, like this. Now, how do we get an ellipse? This is because for different kx, we've got the different direction of the vector. So imagine if we, at time 0, you take a snapshot. If you take a snapshot, the E vector for this x position is pointing here, the E vector is here, and then all that, right? So if you take the snapshot, you got all the vectors all pointing in the round direction. And then if you join all the arrows with the line, you get the helical shape. Yeah, so this one is more close to the DNA shape. Last time you guys were mentioning, right? So this one is really, you got the helix, right? Like the lines joining the helix. Although it's not exact, mathematically it's not the same curve, but you can sort of see the similarities between the two. Yes, the arrow is, so this arrow is E1 plus E2. Remember, what is E? E is this plus this, so it has a Y and Z components. So yes, so this is E1 plus E2. And of course E1 plus E2, so this will give me the the Z component, and this gives me the Y component. And as Y and Z component will change according to this formula, but no matter how it changes, we have proven that this square plus this square is equals to 1. So it has to satisfy this equation on the YZ plane. So this is an ellipse on the YZ plane. So we conclude that the position pointed by the arrow always lies on the ellipse. And furthermore, if these two magnitudes are the same, it's just adjusting the ellipse until it looks like a nice circle. So the coordinates always lie on the circle. So that is basically the elliptical polarization. Okay, so yeah, pretty straightforward, right? If we keep track of what is happening with the E1 and E2. So just follow what happens to E1 and E2. Yeah, so hopefully, like ellipse, and last week we used geometric series On Wednesday, I'm going to talk about divergence theorem and Stokes theorem. So this is, yeah, this is like to show you guys that every topic of calculus 1 and 2 is being used here. Well, as every topic in calculus 2 at least, right? Almost every topic. Okay, so how's my system? I'm recording. The sound is okay. Yep. Okay, so that is the two kinds of polarization. And one last thing to talk about is, let's look at the intensity. So let me remind you about the intensity. It has been at least 1 or 2 weeks, so let us recall a few facts about intensity calculations. Okay, yeah, intensity calculations. Okay, intensity is the average. So to get to get intensity, we need the magnitude of the electric field of E, right? So I got E1. Well, the E total, not E total. So the E1 is just E1 cos kx minus omega t, and then what was it? J direction, and E2 cos kx minus omega t plus the phase difference in the k direction, and I want to get the magnitude, right? So I need to get E max. Okay, so E max, well, E max is just the magnitude of E. So it's just this square plus this square, and then you take the square root. So this one, I think everyone should be okay with this. We have been calculating magnitudes many times already. So nothing new here. No new formula here, just getting the magnitude, right? And then we take the square root. And what we actually need is just the amplitude square. So the E max square is just E1 square cos square kx minus omega t, and E2 square cos square kx minus omega t, right? So I got the x component and I got the y component. And how did we come to the idea of intensity in the first place? Well, we started with the idea of the energy transfer per unit area, right? And this energy per time is giving us the amplitude. So to do that, we were using the pointing vector. So again, reminding, just a bit of a recap, the magnitude of the pointing vector S, right, is 1 over mu E cross B is, well, you can do the calculation. In fact, you should do it as a practice and revision, just to remind yourself and just to get used to it, right? How do you get B? From E, you put everything together, you calculate the cross product. We did this in the previous class. What we have found is the magnitude, okay? The magnitude is C epsilon 0, and then the amplitude of the electric field. As long as this is a sinusoidal electric field, you are going to get this, okay? And this is E max square, but E max depends on these two, is the sum of these two terms. So is C epsilon E1 square cos square kx minus omega t plus C epsilon E2 square cos square kx minus omega t plus the phase difference. This is the instantaneous magnitude of the pointing vector. It changes over time. To get the intensity, we need to take the average of this function, right? So we need one more step. Okay, so I bet most of you have forgotten this already, right? There's many steps to calculating intensity, so it's good to have a reminder here. Intensity is the average of S over a period, right? So one period is 2 pi over omega. Remember this? Okay, so the intensity is just the average of S over one period. That means 1 over 2 pi over omega, integral from 0 over 2 pi omega of this function. and we just get C epsilon E1 square cos square kx minus omega t, integrate with respect to time, and yes, also do it for this term, C epsilon E2 square cos square kx minus omega t plus phase difference, integrate this with respect to time. So what we have found is that if I mix two different lights, the intensity is just the sum of the separate intensities. Right, so basically this is intensity of E1 light plus the intensity of the E2 light. Okay, so it sounds like not very surprising, but I'm taking this chance to recap a few things about intensity, and we will use this later when we talk about the polarizing filter, which is the next topic we will talk about next. But at this stage, does anyone have any questions? Emax2 missed the phi. The phi is here, the phi is here. Oh, this one, yes. Yeah, thanks. Correct. The phi is here, the phi is here. But after you perform the integration, so the phi is not important for the intensity. It is important for the shape of the polarization. And now, because I think some of you have been talking to me about quantum mechanics at different times, right? So now is a good chance to mention that for quantum, especially quantum teleportation, quantum entanglement experiments, people consider the polarization of light as a quantum state that can be entangled and is used for quantum cryptography, quantum teleportation, and what was it? Quantum cryptography, right? So what they do is they transmit information using the polarization of light, and then the data that is transmitted is encoded in the polarization. So it's like vertical polarization and horizontal polarization. That serves as your zeros and ones as your data that is being transmitted, and it is a quantum state, right? So right now we're just treating it like an electric field, but if you take the photons, they are quantum states. So what you can do is it is under quantum superposition, and the superposition of all these different light can be transmitted from one sender to the receiver, and this is how you can do your quantum information experiments, right? You can have entanglement between the polarization of light, and the reason why quantum communication is very popular is because it is one way to guarantee secret communication. So what happens is, if you want to transmit a secret information from person A to B, you must ensure it's secret. So when the B receives it, what they want to do is they want to check whether someone has stolen the information, right? And in quantum mechanics, you learn that if an observer makes an observation, you are changing the state of the system. That is from quantum mechanics, right? Quantum superposition and things like that. So when you check your data, you can actually detect whether someone has stolen that information as well. So that is kind of interesting. It's really using the fundamental aspects of quantum mechanics, and it is one of the hot topics for nowadays in the past few years. Quantum Tenji, yes, yeah. So this is the challenge that people are trying to do right now, because transmitting secret information, we do that all the time, right? Especially nowadays, people do online banking. So online banking, you need to type in the info. How do you know that when you type the info through the internet, you are sending in your data through the internet? So people can actually steal your info, right? Steal your password and things like that. Right now we have ways to use our password, right? The 2FA token kinds of things. That is one way to ensure the secret. But currently, if there is a computer that is strong enough, and powerful enough, they can actually break your password. So they can actually hack your password. So it's not completely safe right now. But if you use quantum information, regardless of how strong the computer is, you can't hack the password. So that is one of the interesting aspects of quantum communication, and this is why it's a hot topic nowadays. Only 20. Yeah, so you must keep your $20 safely in your bank account, right? And therefore your password must be secure. Precious money, so don't let anyone steal it. So that is the idea, right? So, and this gives I would suppose this gives an idea of a career path. If you like, the common question of student is, what job will I do if in the future, if you don't want to be a lecturer or a full-time physicist, right? Yeah, you will be working in banks because people will. This is in the future, right now not so much. Right now there's only a few companies that are doing this, like those IBM, the Bell Labs. Those are private companies, but they hire physicists, and they are trying to work out those quantum experiment kind of things. So IBM and Bell Labs are the ones that I heard of. By now there are some new companies starting up here and there, but it gives an idea of where is the future direction of this research. Okay. What time is it now? So the next topic will be polarizing filters. Like I said, right, polarized light can only be produced by ideal sources, and most light, like the light around me right now, is unpolarized light, except for the light coming out of this computer screen. LED light is polarized. So this is an issue. So usually only ideal sources can produce polarized light. Okay, and reminding you again, polarized light means all the electric fields are oscillating along the same direction. Okay, so this is the issue that we are having now, and just to give us an idea of what is the ideal sources, laser is an obvious one, and then LED light, okay, the light emitting diodes, or your computer screen, so it's a LCD screen, and things like your phone, right? So your phone is a LCD screen. They produce light in certain fixed polarizations. So when they produce a polarized light, that means everyone is oscillating along the same direction. Okay, so something like this. So when I draw it this way, this is everyone is polarized along the this is polarized along the y-axis, right? And in general, it could be in some other angle. So let maybe something like this, right? That means in my y-axis, my direction of polarization is here. Like this. Okay, so let's take a random example. So let's say this is 20 degrees. So we say that this light is polarized at 20 degrees with respect to the y-axis. So these are the polarized light. Okay, and this is the light that we have been studying. So if I mix two different polarization, you get circular polarization, linear polarization, this. Unfortunately, not all light sources can produce polarized light. So this is because many light sources are, well, let's say not ideal. Okay, so not ideal. That means not ideal. And not ideal light sources, some examples may be black body radiation, right? Thermal light bulbs, or just say light bulbs, candlelight. So all these things, they produce light, they are not polarized. So what does it mean by not polarized? That means that the direction of E is a random mixture of directions. Okay, so think about like black body radiation. You have one object emitting this light, and then another part of another object emitting another light. Like even your light bulb, right? So your light bulb has a wire, and then you turn on the electricity, it glows it glows and emits light. But the different atom emits different light at different directions. So at the end, the light that comes out is actually a mixture of many different directions. So you're just gonna end up with a light that is is no longer a nice direction. It's just a random mixture. Okay, so if I draw my y-axis here, my x-axis here, my z-axis here, we notice that the direction of E is random. In other words, previously when we talk about polarized light, we take E1, E2, we have a sum of two vectors that are having specific directions. But now I just have a sum of don't know how many vectors. We can't even tell because we have different atoms emitting at different directions, at different positions. Everything is all a mess. It's a huge mess. It's chaotic, each in random directions. So these are called unpolarized light. Okay, so this is what we mean by unpolarized light. Six-digit password product, two-digit money. Still doing physics but in bank. It does sound kind of weird, right? But when we have time, ask me about quantum finance. That is another whole interesting stuff. Yeah, quantum finance is another thing that physicists have been working on. Because the theory of finance, you can actually apply quantum mechanics to the theory of finance. And so for the physics students here, for the math students here, I mean, the Malaysian math students have a choice to take a physics course or the economics course, right? And also financial mathematics is one of the options, right? So financial mathematics is a whole new branch of area, and quantum finance is actually applying quantum mechanics to financial mathematics. So all this like stock market prices, oscillations, and things like that, time series. Yeah, there's a whole bunch of area which I'm not familiar with. So this is unpolarized light. Okay, and that is a problem. Like I said, you know, for your quantum encryption experiments for your bank password, even though it's just two-digit money, but it's still your money. You want to protect it. You need to use some kind of what we want is for experiment is to have polarized light, basically, right? So if you only have an unpolarized light source, can you still create a polarized light out of it? The answer is yes, using the polarization filter. So this is the experimental device that is used to produce polarized light using from an unpolarized light source. Okay, so to produce this, we use a polarizing filter. Polarizing filter. So a polarizing filter is just some device that has some direction. So let's say my direction is here. Okay, so this is a device that has some fixed direction. So this is my direction of the filter. So okay, and let's say this is my optical axis. So if I have some light that is all the random direction, right? By the time it pass through the filter, it will let this light come out. So so the light will be all in this direction. So this is my polarizing filter. So my electric field all will be nicely polarized once it comes out. Okay, so this is the device. How does it work? I guess we will not cover this. It depends on a lot of the material properties and the things like that. So a bit complicated. But in any case, I guess now is a good time to take a break. So after, when we come back from the break, we will see the consequences and play around a little bit more on the consequences of the polarizing filter. Superposition of 0 and 1. Yeah, quantum finance. So this is what this is like probably one of the different various aspects of it. Okay, so let's take a 10 minutes about this. Tensor, something like differentiable manifolds. Yes, basically yes, you need differential manifolds. Differentiable manifold is just a set that is like a curved space, you know, from my in a simple way. So for math majors, you will learn a more differentiable manifolds. It's like a curved space. So it's a simple way to understand it. It's a curved space. So it's a space with some kind of curvature, and this is why in general relativity we use differentiable manifolds all the time, because the theory of Einstein is to say that gravity is the curvature of space, and it has many mathematical properties related to it. And yeah, so it is in math, it is a third year course, I think, differential geometry. You will learn this in differential geometry. You need to do integration, all that. Correct, right? You did this, right? For quantum mechanics, you want to find the probability of the electron is here. You need to perform an integration. So that is what I meant. But now we shall come back to polarization filter. So now we know, okay, the light comes in, shine through the filter, it will come out based on the direction of the filter. And in the experiment, you can actually turn this setup. So you can actually rotate this to match different directions that you want. But what happens to the direction? So let us look at this. So initially, right, this light is having, well, random direction. So how can we study this random direction? Well, because it is random and because it is a vector, so we will take advantage. Well, no matter what random direction, what random vector, a vector is still a vector, and all vectors can be resolved into two perpendicular components, right? Even if it's random, right, it could be this way, it could be this way. No matter what is the direction, it always has a horizontal and a vertical component. Okay, so let me put one of the direction is this way, and then the other direction is perpendicular to it. In other words, what I'm trying to say is two components. Okay, so two components, fine. But how much is in each component? Well, this is random, and because this is random, on average there is like 50% of them are in this direction, and another 50% is in the perpendicular direction. Okay, so yeah, right. So let me call this the E1, and let me call this E2. So the intensity of the input is what we calculated earlier, right? So the incoming intensity is a mixture of directions, but after you resolve it, 50% is here, the other 50% is here. So this is the intensity of the direction that is parallel to the polarizer, and this 50% is going to be perpendicular to the polarizer. Okay, so this is half, right? And to emphasize, since this is it's random and this is 50%, so this gives a half of total intensity. Okay, and this part is perpendicular to polarizer. So this part is going to be blocked by the polarizer. So this part doesn't come through. Okay, so this part will be blocked, right? Only the parts that are parallel to the polarizer will pass through, and on average, because it's random, so it's 50% of this will pass through, right? So it's just random, just like random, pure randomness. 50% will be this, another 50% will be this, right? It's not one higher, not one lower, it's equal. So 50% is perpendicular, will be blocked, and the other 50% will pass through the light. So the light that comes out is going to be half. So the intensity of the output is going to be half of the original intensity. Okay, so this is for I should write it more separately. The intensity of polarized light coming out. So intensity of polarized coming out is intensity output is half of the input, which is the unpolarized light. Okay, so it's half. Okay, clear so far? We just assume it's 50%, yeah. Because there's no reason why it should be one side favoring more than the other, right? Because it's random. It's all, yeah, there's no reason why one to be more than the other. So that's why we assume it. Okay, so this is what happens to the polarizing filter. Because it's polarized, it's random, so half of the light will be blocked. So what comes out will be not as bright as before. And okay, yeah, yeah, yes, that's true. So this is the common jokes between physics people and math people, right? Because physics is like, oh, assume this, assume that. Well, we have to. If we don't assume, we cannot make any progress. We will be just stuck at this problem, and we cannot gain any extra information. So usually, yeah, we can't make it's not a choice. Okay. And when we relax assumption, when we do calculation, yeah, you guys see all the calculation becomes a huge mess already, right? So that is also another reason why. So that is what happens if I shine unpolarized light through a filter. So now we start to play around. Now that we have this device, so we can start playing around with it. So let's say we have two filters. Okay, so we take one unpolarized light, we shine through it, then what comes out becomes polarized. What happens if this polarized light passes through another filter? So this is what we will study next. So what happens when all polarized light, already polarized, passes through the filter. Okay, so this is what we want to explore next. So now let me draw the filter again. Right, so draw the filter. Let's draw it here, and let's say the direction is at some angle phi. Okay, and this is my optical axis, so the light will be coming through along this direction. So let's say my light is already polarized in this direction. So this is my input light, and my electric field is along the y-axis. But my filter is not on the y-axis, it's this direction. Right? So the polarizer direction now is at some angle phi from the y-axis. And because, as we can expect, this is a polarizing filter, a filter only allows this direction to pass through. So the light that comes out will be this direction now. Okay, so what is the intensity of this incoming light? So let me draw this more carefully. Remember that any vector can be resolved along this direction. So if the light, okay, so if my light, well, the direction of my filter is this direction, right? So if my original electric field is this way, and then the angle phi is this way, so the component along this direction is going to be E, the input magnitude, cos phi. Am I right? So this part, E sin phi, will be blocked. So this part will not pass through. Okay, so I'm going to let E in be the amplitude of the incoming light. Right, the direction originally was y direction, amplitude is E input, but if I pass through the filter, only this component can pass through. So that means the output will be having the amplitude of E cos phi. Okay, so yeah, just to make it more clear, right, what is happening here is component, this component, E input cos phi, is parallel to polarizer. So this part passes through, and the other component, E in sin phi, is perpendicular to polarizer. So this part is blocked, cannot pass through. Okay, so that means the output will now have the intensity, well, amplitude reduced by this. So we can now calculate what happens to the intensity. Let's find out, right? Intensity. The intensity of the output is just half C epsilon and then the amplitude, right? So amplitude square. But this amplitude is now half C epsilon. The amplitude is now this thing square. So it's the E input cos phi square. So what we have find is that my output intensity is just half C epsilon, the E input square, cos square, phi. And this is just the intensity of the original light coming in. So this is the input intensity. So we call this I in. And the equation that we derive here is the output intensity is just I in cos square phi. So this is the equation that what happens to the intensity when you shine polarized light to the polarizer. Contrast this with unpolarized light. Where was it? Unpolarized light, no matter, unpolarized light is random. So what comes out is definitely half of the unpolarized light. But if the light is already polarized, then it depends on the angle. In particular, if the angle is 90 degrees, then no light comes through. Okay, so this is what we call Malus's law. Okay, so what happens when polarized light shines through? Okay, any questions so far? Okay, so now we know what happens. No matter what kind of light that comes in the polarizer, we know how to calculate the output, whether it's polarized or unpolarized. So let's see how it works in an example. So let's go to 9.7.1. So questions related to polarizer is usually very simple because the equation and the concept is all very simple, right? After we understood it. So if we have an incident unpolarized light intensity I0 incident, as shown in this figure, find the intensity transmitted through the first and second polarizer if the angle between the two axes is 30 degrees. So that should be pretty straightforward. So let's solve this. I will show you the usual way for me to solve this by drawing the picture, because once I prefer to draw the picture, then it gives me a very clear idea of how to solve the question. Optical axis first. So this is example 9.7.1. Optical axis along the horizontal direction. Okay. So according to the question, my first polarizer and the last polarizer is at angle 30 degrees with each other, right? So let's say my first polarizer is this direction. Okay, and then my last polarizer is in this direction. So previously was fine. Okay, so I have the random unpolarized light coming in. The original intensity is I0, but what comes out through the first polarizer is going to be now polarized. Okay, then from what we have been, why is it so dark? From what we have been discussing so far, the intensity after passing through the unpolarized light is half of this, right? So this is the intensity at this step. Okay, and then now I pass through another polarizer. So this is already polarized, coming through another polarizer. This polarizer is in this direction, so the light coming out should be in this way now. But according to Malus's law, the intensity of this must be the previous intensity cos phi, and the previous intensity was half I0 cos phi, and actually phi is 30 degrees. Cos square, I forgot the square. So I got half I0, 30, cosine 30 is root 3 over 2, am I right? So this is 3 over 4 times 2, 8 I0. Right? Yeah, 3 over 8 I0. Yeah. So this is the output intensity. Right? Very simple, very straightforward. So these polarization topics are pretty straightforward in that sense. Okay, any questions so far? Yeah, so that's it, right? So that's the topic for polarization. Okay, of course, right, we only just scratched the surface of all the topics we have been covering. Polarization, there's many things you can play around with. Electromagnetic waves, radiations, there's many things to study. We only just touched the surface very briefly only, and there's more things to cover in future courses. But for now, there is still a few things I haven't finished talking from last class because we ran out of time actually when we're talking about interference and phases. So now we got plenty of time left, so let us finish this topic. So yes, so this is it for polarization. Now let's go back to interference and phases. Back to interference and phases. Okay, so previously what I was saying halfway, well, I was talking last time, how do you calculate the phase difference? Initially, if I got the light that is cos kx minus omega t, and then if I travel a distance of L, then the amplitude here becomes cos kx minus omega t plus kl, right? So this part happens after it travels a distance of L. And then another thing I was mentioning is what happens if there is an object of refractive index n. Okay, usually we know that the total distance is L, so we will split this into x1 and into x2, and this is the thickness of this material, right? So the total distance is just L. So what happens to my refractive index? So if my initial phase is kx minus omega t, and then over here it will become E cos kx minus omega t, and then after traveling until now, it will have a new phase difference, and this new phase is calculated in this way, right? So we just do it step by step. If I travel a distance of x1, the phase change will be kx1, and then I'm traveling this distance, the phase change is k times the thickness, but inside this material, the wave number changes to nk. Remember this? And then now I travel another distance, this is kx2. So these two pieces I put together, kx1 plus x2, and then this is nk tau. Now what is this? x2, well, x1 plus x2 is just the total length minus tau, and I can factorize the k outside, so I got L minus tau plus n, k come out already, tau. So my phase change after traveling through this block is plus n minus 1 times the thickness. So this is how we calculate the phase change, right? So this is kl plus n minus 1 tau k. Yeah, whichever formula you prefer to use. Okay, so that was what we were talking about last time, right? This is page 8. Then why did I mention this is because we want to calculate the interference that if I put a piece of material in front of here. Right, so L1, L2, okay? So if my initial phase is E cos kx minus omega t, and then over here is E cos kx minus omega t, then this part I want to know what is E1 and I want to know what is E2. So E1 is traveling this distance, and then I got this block of thickness tau, right? So the phase here is E cos kx minus omega t. I just do everything accordingly. It's just basically plus kl1 plus kn minus 1 tau, and then for the second one is, well, there's nothing, so omega t plus kl2, and then nothing. Okay, but I think one of you mentioned earlier that yeah, you can now have a general formula. In fact, I can put a second piece here, thickness 2, material 2. Then if I have thickness 1, material 1. So thickness 2, material 2, I just do everything accordingly. So this is K, N2 minus 1, tau 2. So this is thickness 1, material 1. So you can play all kinds of combinations, right? And then the phase difference. So the phase difference between E2 and E1 is you take the difference between this. So the phase difference between E2 and E1 is what? Well, take this minus this. So what we found is K L2 minus L1 and then this minus this. So I got well, there's a K overall factor, and then I got N2 minus 1 tau 2 minus N2 minus 1 tau 1, right? And then once I found the phase difference, I can find the constructive interference, right, and destructive, and so on and so forth. So if I want constructive interference, this is m pi, or if I want to have destructive, it is an odd number and then pi, and then you just calculate the general formula. Okay, so it depends on the phase difference, but once you have found the phase difference, it should be straightforward to get the constructive interference. So this one is no problem. Okay, so this is what we have been talking about so far. Well, once we know how to handle the tau, it should not be so scary anymore, right? So that is why we introduce this calculation here. Now, so this is just recap everything that we have been that I have mentioned before. The one that I haven't mentioned yet is, well, we assume that we did make the assumption that the starting phase is the same. What if they are not the same? Okay, so this is the question now. So what if S1 and S2, so this is the light source 1, light source 2, does not have the same initial phase. Okay, so let's take the double slit again. So let's take light source 1, light source 2. The distance between the two is, of course, is just d. Then my initial phase is cos kx minus omega t, and then the initial phase here is cos kx minus omega t. So if most of the time we have been assuming they are the same, but what if they are not the same? That means there is a difference here. So this number, yeah, there's some extra number, so that these two numbers are no longer the same. Okay, so now both of them are interfering on this light source. Okay, so distance L1, L2, fine, right? Then how do we calculate? Well, we just incorporate this distance. So when the light has traveled a distance of L, then this light will have cosine kx minus omega t plus KL1. Okay, so this is for light 1. Light 2 is E0 cos kx minus omega t. Got this thing here. And then this is the starting phase. And then it traveled the distance of L2. So KL2. Okay, so now to find the phase difference, these two parts are the same. We just take a difference of this and this. Okay, so the phase difference now is now calculated accordingly. Is this minus this. Okay, so phi is K L2 minus L1, and then there's this extra thing. So it could be positive phase difference, negative phase difference, whatever number this is. Then yeah, now how about constructive interference? Right, so I want phi over 2 is equals to integer times pi. So that means this thing plus delta, so half, right? So half of this and then half of this must be m pi, and k is just wave number, so it's 2 pi over lambda. This is half L2 minus L1. This is delta over 2 m pi. So this thing can cancel, right? And I can bring this to the other side, so I got m pi minus delta over 2, and let me take out the factor of pi. So pi is m minus delta over 2 pi, and on the right hand side I got pi over lambda L2 minus L1. So now I can cancel the pi everywhere, right? And L2 minus L1 is d sine theta, so d sine theta is just m minus delta over 2 pi and then lambda. Okay, so this is my new formula. And if I'm taking sine theta is approximately y over the distance, then I found my formula for y as well, which is delta over 2 pi lambda distance over the small d. So the interference pattern has now shifted by this amount. So yeah, basically yes, just playing around with the phasor, because it's the phasor that determines all the phenomena, right? So which is good, right? You just need to do these two things: phasor, intensity. Once you master these two, yeah, there's not many complicated things here. So it's just this specific thing. Okay, so this is what happens when there is a phase difference between the two light source. I probably repeating this many times already, but you know, the reason why we do this is, yes, I'm showing you how to do the calculations, and my advice, which I have repeated many times, is try not to just memorize this formula, and then go to exam, because exam can manipulate the situation a little here and there. So once they manipulate the situation a little bit, the formula will change. So the better way to study is to understand the thinking process of how, from this situation, how to find the phase difference. And once you found the phase difference, then you can get the correct formula. Okay, so yes, no more memorizing formula, because this is no more primary school or high school, secondary school, I mean, right? Because I know secondary school most of the time is relying on, yeah, those kinds of memorizing formulas. Okay. So am I recording? Yes. Primary school. Yeah, secondary school, I mean. Yeah, it is kind of true in different meanings that, yeah, things are manipulated in the real world differently. Okay, so let us apply all this reasoning to the tutorial. So let's do the tutorial question. And I think let's jump straight to question 14 before we run out of time. For some strange reason, in the last few tutorials discussing one question, I don't know why I spent so much time. So let's jump to question 14. What is question 14 about? So let me show you. So it's this problem. I have 4 identical radio broadcast towers, so basically EM wave. The y-axis is here, and then the positions are here, right? So the plus and minus 5, plus and minus 15. That means each radio tower are separated by 10 meters as given here. Okay, so that the distance are 10 meters apart. All 4 towers broadcast at this frequency and initially in phase. Okay, And then there's a road here, and the distance is 10 kilometers away. So if you drive from y0 upwards, what is the position of y such that we get the intensity maximum? So from this information, we can calculate the wavelength and everything. But yes, what we want to answer is this. If the observer starts at y equals to 0 and begins going in this direction, what is the position such that the intensity reaches the maximum because of the constructive interference? 4 towers, right? 1, 2, 3, 4. Okay, this is not Lord of the Rings. Oh, yeah, don't worry, final is very easy. Okay, so yes, let us calculate this using the method that we have been doing so far. So the distance from the tower to the road, which is, we treat this like a screen, is 10 kilometers, so it's 10k meters. And the frequency is 100 megahertz, so it's 10 to the power 6. So from this info, I can actually get the wavelength. The wavelength is just the speed of light divided by the frequency. Speed of light is this. Frequency is 100 times 10 to the power 6. So this is actually 3 meter wavelength. And the distance between them, small d, is just 10 meters. Okay. So firstly, is everyone is in phase. And let's calculate the interference. So when I have multiple slits, what do I do? When I have 2 slits, I calculated between the 2 slits, but now I have 4. So I will calculate pair by pair, right? So let's do this. So firstly, let us calculate the interference between 1 and 2. Okay, so between 1 and 2, if I want to have constructive interference, we find the phase difference, right, between the two. So the phase difference is just traveling the extra distance of k. The distance between the two is just d sine theta. Okay, and if I want this to be constructive, this must be equals to 2m pi. Am I right? So k is 2 pi over lambda, d sine theta is here. This is 2m pi. So I can cancel this. This is the same calculation as the double slit. So I find that my y is equals to m lambda d, m lambda, well, now it's called L, over the distance. Okay. So the position for constructive interference is, depends on m. It will give you the corresponding values of y. So m can go from any integer, but let's start with minus 2. So if this is minus 2, this is 2 lambda L over d. Minus 1 will be minus lambda L over d. 0 is 0. 1 is lambda L over d. 2 is 2 lambda L over d. And it can continue on so forth. Okay. So then, this is just the interference between the first two. So I want constructive interference between everyone. So I want to make sure that this pair also has constructive. Okay, so now let's consider between 2 and 3. So 2 and 3, the phase difference is still kd sine theta. And if I want this to be constructive, is still 2m pi. So the calculation, so it will give the same formula. Okay, so m, y, and then the same thing, right? So minus 1 gives you lambda L over d. 0 is 0, 1 is lambda L over d. And then finally, between 3 and 4, same thing. Why do I emphasize this when I already know it's the same? Because when we go to the next question, the distance not the same, so you need to be careful. But this is the method to do it. Okay, so we calculate between all the pairs, and then we get the same formula. So m, y, minus 1 minus lambda L over d. 0 is 0, 1 is lambda L over d. If it's 2, it's 2 lambda L over d, and so on and so forth. Okay, so there is a common value between, actually all the values are common, but this position is the same position for constructive interference between all pairs. So the position for constructive interference the position for constructive interference is of the first constructive interference after the zero is, well, it's just lambda DOL, right? So we just plug in the formula. Lambda was 3, L is 1000 meters, and then this, so is 300 meters. That's it, right? So this is the answer for part A. Actually, we are using the same formula as the double slit because everybody is in phase, so this is the same. The maximum is the same. Interference, yes, it can be applied to sound wave. Anything that's a wave is applicable, right? So EM wave is a wave, sound wave is also a wave, so it will have interference. That's true. That's why you got this noise cancelling headphones, I think, right? I think that is the principle to use. But now in part B is where things get interesting. Okay, so I have the 4 radio towers. But okay, so yeah, so they will interfere. I think no need to draw the diagram. Well, I will draw the parallel lines. But they are not in the starting phase is not in anymore, right? So according to the question, I guess I should read the question. Suppose that the 2 towers, another typo, here and here malfunction and becomes half a cycle out of phase. Okay, so there is a phase difference by half a cycle. So what will be the new answer? So let me, to answer this question, it's actually very easy after we write the equation for my electric field. So the light traveling here for E1, by the time it reaches at the point of interference, is going to be cos KL1 minus omega t. This one is no problem. There's no, this is in phase. These two will malfunction, right? So this will travel the distance L1, this will travel the distance L2, this will travel L3, this will travel L4. So the second tower have malfunction. So the second tower will have the equation given by what? Well, I travel by distance KL1 minus omega t, sorry, KL2. But now I have half a cycle out of phase. So half a cycle is half of 2 pi. So it is out of phase by pi. Okay, so this is the half cycle out of phase. We're out of phase with light 1. Okay, how about light number 3? So for light number 3 is KL3 omega t minus, well, there's nothing here. Light 3 is okay. The tower number 4 is different. So I got cos KL2 4 omega t and then another half cycle out of phase. Okay. Wow, I'm running out of time already. So I guess I can go quickly because the rest is in the solution already. The rest is in the solution. So let's calculate between E1 and E2, right? So E1 and E2, the phase difference is just K, L2 minus L1 minus pi. Then for constructive, this number minus pi must be equals to integer times pi, right? And then yeah, and the rest is continue on so on and so forth. Actually, I'm running out of time. I wanted to show you when it's half cycle, right? Whether you minus pi or plus pi, you get the same result. Just that the number is shifted a little bit. But because I don't have time, I'll just synchronize with the solution, the tutorial solution. So in the solution I use plus. So this is plus, and then you calculate, and then you find the common position for constructive interference between all pairs. Okay, so between 1 and 2, 3 and 2 and 3, and 3 and 4. So if this is constructive, and then you find this, and then you find this, that means everyone will be constructive interference, and you just want to find the common positions. Okay, so yeah, somehow for when I start talking about tutorial question, I run out of time. I don't know why. Okay, so in principle, make sure the difference between any E is correct. Yes, because this is the one to achieve constructive interference. Yes, also you don't have to check all pair, because if these two are constructive and these two are constructive, then 1 and 3 already constructive, right? Just a common angle between the two. So if this matches with this and this matches with this, then everyone is constructive. So in that sense, you don't need to check all pairs, because if you actually you realize this when you try to check all the pairs, right? You calculate 1 and 3, and then you realize 1 and 3 is already same as 2, and 2 is already same as 1, then everyone is the same. So as long as there's a common, something like that, you know, I guess you know what I'm saying, right? So because this is the same and this is the same, then yeah. I'm tempted to use the word transitivity, but in math, transitive means something different. It's kind of this feeling, this idea, something in common. Okay, so yeah, I think that's all for today, I guess. So in the Wednesday class, I will finish off by using vector calculus to talk about Maxwell's equation, and yeah, so that will be the Wednesday class. The Wednesday is the next and final class.